So we'll start off with Dr. Tim Smith presenting. So take it away, Paul, or take it away, Tim.
Thank you, Jeremy. All right. Patrick, can you see my screen all right?
Yeah, looks great.
Great. Thank you everyone for attending this webinar. I wanted to take this opportunity to kind of give some updates of, some of the mechanical maturation in terms of getting data for GRX A10. But I always like to start trying to describe, how we came about creating GRX A10. And it really occurred here at NASA Glenn when there was an issue with producing 3D printed combustion domes that needed to operate at very high temperatures, 2000 degrees Fahrenheit, 1100 degrees Celsius. And it had to be 3D printed. And, again, at those temperatures, the type of alloy systems that you can really tap into are pretty limited. A lot of them either have oxidation problems or, printability issues for this application. What we want to do is try to explore this class of alloys called oxide dispersion strengthened alloys. And in case you're not familiar, what an oxide dispersion strengthened alloy is it's a metal that has nanoscale oxides incorporated into the metal part. And those nano oxides allow for large improvements in high temperature properties, stability of the microstructure, and a multitude of other properties like fatigue, creep, oxidation. The reason you probably haven't heard of oxide dispersion strengthened alloys is that they were very difficult to produce a few decades ago. It was a very complex manufacturing route. It was very expensive. But as additive manufacturing matured, it became a new manufacturing pathway that we could tap into to try to produce these ODS alloys. Now, we still had the issue of, okay, how do you take metal powder that you're going to use for your 3D printer and incorporate those nanoscale oxides during the print process? Initially, we had started with ball milling and more conventional ways to produce powder, ODS powder, but all of those are still, again, very expensive, and they led to a lot of issues in terms of printability. Ball milling kind of heavily deforms your metal powder, and it adds to a lot of defects when you try to print it. What we found is that you could coat metal powder. In our case, we use a high energy mixing technique called a resonant acoustic mixer. We could coat the metal powder with nanoscale oxides. So we would kind of mix them together, and during that process, you can kind of see here a SEM cross section of a metal powder. And if you really zoom in, you can see this thin layer of yttria that has adhered to the surface of it. And again, in a chemical map, you get this nice, highlighted yellow ring around the metal powder. And so our thought was, okay, if we could just coat the metal powder, maybe we can then print it and form an ODS alloy through the printing process. What's really nice about this technique is that it is actually amenable to the 3D printing process. Again, when I mentioned ball milling, that heavily deforms your powder, and it really affects the flowability of the powder and your size distribution and things like that. With this coating technique, what we found is that in many instances, it actually improves the flowability of the powder. We've been able to take metal powder that wouldn't flow in our printer and print. We could coat it with these nanoscale oxides, and all of a sudden it flowed well enough to actually print with. So, coated metal powder feedstock is actually, very amenable to the 3D printing process. So we initially started our ODS alloy development work just looking on a base alloy composition of nickel, cobalt, chrome, and equal atomic metals. There had been some literature that kind of showed promising results with nickel, cobalt, chrome, the metal, and it was very printable. And so it was a great composition to kind of do a foundational study with. But at elevated temperatures, there really isn't anything that special about nickel, cobalt, chrome. And so what we wanted to do was take that base alloy composition and add other elements in it to trying to improve the high temperature properties of this alloy. And so we kind of set 5 goals here. which was, how can we maximize the solid solution strengthening of the alloy while maintaining the solid solution matrix? We didn't want phases popping in and out as you 3D printed it, heat treated it, or used it in applications. We knew we needed to strengthen the grain boundaries. At really high temperature, your grain boundaries almost start to begin to act like defects, and a lot of your failures will occur along them. And so if we could add stable grain boundary carbides, we would suspect it would help improve our high temperature properties. And again, we want to avoid any other grain boundary phases that would be unstable, that would cause issues. And we wanted to maintain the printability of the nickel cobalt chrome system. So one way to kind of do this is, if you at least kind of reduce the freezing range, the temperature between the liquidus and solidus, you can kind of expect that you have a better chance of having a printable alloy. So we set out these 5 goals. So we used thermodynamic modeling to come up with a new alloy composition based around that nickel cobalt chrome foundation that we started with. And you can see the nominal composition that we came up with at the bottom here, which we were calling GRX 810. And so we'll dig into some of the microstructural results. As you can guess, we were able to take that coated powder and print with it really well, and we were able to disperse the nail oxides during that printing process. And so these are kind of some of the interesting, microstructural features that we've seen in GRX 810 that might, give reasons for why we're seeing so much better properties than even other ODS alloys that we've tried to print recently. One is, there does appear to be some carbon segregation between the oxide particle and the gamma matrix. You can kind of see it here in this TEM. So this is, high resolution, so 100 nanometers. We also see grain boundary segregation of tungsten and rhenium. So these are heavy solute elements, and we think that helps with grain boundary strengthening beyond just the carbides that you can also see here in niobium titanium carbide. So we think those two together are helping to strengthen our grain boundaries at elevated temperature. And what we've also noticed is that in the matrix, we've added all these different elements, but they all still maintain this solid solution. We don't see any type of local ordering at the atomic level. Now, something that's been very interesting that we've recently found, and so we're digging real deep now into the characterization here of ODS alloys. But when we start coating these powders, we always start with cubic yttria. So that's the crystal structure of the yttrium oxide. It's stable. Crystal structure is cubic. It's almost how you would assume yttria will be. And in fact, when we produced nickel cobalt chrome ODS and 3D printed it, when you look at it in the microscope at very high resolutions, sure enough, it's cubic. And you actually can see the facets of the single crystal cubic structure here. Now, what's interesting is that for GRX 810, the yttria is no longer cubic. It's a trigonal crystal structure, which is a very unique crystal structure, and one, according to literature, that just is not stable at room temperature or even at elevated temperatures. It's really only stable under very high pressures, I think 12 gigapascals. And past studies, as soon as we release that pressure, it reverts back to a different crystal structure. And so there's very little research on this specific crystal structure, but for some reason, we're forming trigonal yttria oxides in GRX 810. Now, I mentioned, that carbon segregation at the oxide matrix interface, and we're starting to explore, if carbons may be, influencing that. But the question is, all right, we've dug real deep here. We're starting to look at oxides at the atomic level. Does this actually mean anything? And I think it does. And when you're making an ODS alloy, the goal is almost always try to get as much nanoscale oxides as you can that are as fine as possible. You want them to be maybe even 9, 10 nanometers in diameter. The finer, the better for creep properties. And when looking at all this TEM characterization, we started measuring the oxides that we saw in the nickel cobalt chrome base ODS alloy and in GRX 810. Again, the different crystal structures. And what we found was GRX 810 had a significantly finer oxides distribution than what we saw in the nickel cobalt chrome ODS. And so this might have, you know, be a result of just having this different type of crystal structure. For anyone who's, material science folks out there, what's interesting is the trigonal is actually metastable. And once you free it from the matrix and you characterize it under that electron beam with the microscope, you will actually see it transform back to a cubic during the characterization step, which is really fascinating for us when we're looking at it, but also kind of annoying when you're trying to take pictures. But so that, that right there is, just some more of the things that we're starting to discover about GRX-810 that kind of helps it stand apart from other ODS alloys going forward. We've also done mechanical testing for a multitude of properties, which I'll discuss, but we've also taken tensile properties all the way out to almost its melting temperature. In this case, 13, 16 degrees Celsius. And I like this figure because it does kind of give you a sense of, when does GRX-810 start to become stronger than other, conventionally used superalloys. And, when we're picking on the conventional 3D printed alloys like 718, Haynes 230, 625, it's really between that 900, 1000 degrees Celsius where you start to see GRX-810 become significantly stronger. But what's interesting is that you never really kind of hit that cliff that a lot of other superalloys have before they melt, where they lose all their strength. And in fact, by the time you hit 1200 C, you're starting to get tensile properties that are, closer in line with what you might get with a single crystal. Again, single crystals aren't usually used at those high temperatures without cooling, but it just kind of shows, how incorporating these nanoscale oxides, can kind of really push the possible operating temperatures for these alloy systems. And by the time you hit the 1300 C, I was even surprised by this. There actually is some, tensile strength left in this alloy, and we're talking 98, 99% of its melting temperature, which is really, I think remarkable. And we've done, other studies here at these temperatures, and I'll kind of show that. But I'm more and more convinced that that this is real here. We have looked at orientation effects, and I have a lot more data. Our hope is to kind of get a data sheet out here very soon. But just some general trends that we saw. For most temperature regimes, the horizontal orientation is usually stronger and just as ductile as the vertical orientation. And that goes all the way up to even 2000 degrees Fahrenheit, 1100 degrees C. Again, both orientations at those really elevated temperatures are still ductile. You do see a little bit reduction in the ductility in the horizontal orientation versus the vertical one, but still a very ductile material even then. And I will say the differences in strengths does start to converge as you go up to these very high temperatures. We've done some new oxidation studies, and so we're looking at cyclic oxidation at 1100 C 1 hour cycles, 1200 C 1 hour cycles, and 1300 C 1 hour cycles. And I'll be honest, we've got a multitude of other alloys that we wanted to get together and try to compare it with. And I've had some colleagues ask, well, why did you use these alloys? A lot of the reasons is we had them on hand at the time. But what we wanted to do was make sure we were definitely comparing it to 718 and 625. But we wanted to also add some alumina forming superalloys like single crystals, B1900 and SC180. When it comes to oxidation, alumina is really your gold standard in terms of protection. And so, with GRX-810, there's not enough aluminum in it to form an alumina layer. And so we're kind of relying on the chromia, but also the nanoscale yttria for our oxidation protection. We kind of want to see, where does it compare between the alumina formers and the chromia formers at elevated temperature. At 1100 C here, this is 718. This is GRX-810, the yellow curve, and the gray curve here is the B1900 alumina forming serum crystal. And you can see, GRX-810 appears to kind of be closer to that alumina former than the 718 chromia forming alloy. And we expect it's because of those nanoscale oxides. At 1200 C, more or less the same trend. It's kind of bridging the gap between those chromia formers and the alumina formers. But what's interesting is when you get down to the 1300 C 1 hour cycles. This is a very extreme environment. all of these alloys are, losing weight at a pretty rapid amount each cycle here. But GRX-10 definitely forms a much more is a much more stable alloy at this temperature, and it performs better than even the alumina formers. And it might have to do with the fact that these superalloys are also starting to melt, where GRX-10 isn't. But if you this is a great comparison, I think, of just how much more stable the GRX-10 microstructure is to the more conventional superalloys. This is GRX-10 on the top here after 10 cycles at 1300 C. You can see, there's a thin thin oxide layer that is formed, but otherwise the microstructure is very stable. We don't see, gross porosity forming or anything like that. Whereas 718, you have this huge oxide layer that is formed, and clearly the microstructure has, started to fall apart, either through incipient melting or some other mechanisms, maybe just massive diffusion to form the oxide layer. And so clearly at these conditions, 718 would have no structural properties of use here, whereas GRX-10, it would still be usable. We also looked at the oxides in these, and we actually see no evolution of oxide growth in terms of nanoscale oxides growing or evolving, and so they are very, very stable up to the melting temperature of GRX-10. I did want to give a kind of a background on ODS alloys. One of the things that really plagued this group of alloys, and beyond the cost, was they had an issue with creep ductility and the transverse orientation. And so if you imagine our 3D printed alloys, we are getting kind of that more columnar grain structure, and so this would be our horizontal creep properties here. You would expect there to be a creep debit because the grain structure is non-optimal for creep. Again, these grain boundaries are like defects, and if they're orthogonal to your load direction, you're gonna fail quicker. But with these ODS alloys like MA754, if you look at the study, you can see the creep ductility issue that exists, where they're failing at 0.2% strain, 0.6, 0.4. And because of that, it became an issue where you have poor defect tolerance basically for these alloys. The parts will fail if they have any type of load in that direction. And so it really plagued the application use for these alloys. So I want to compare now nickel cobalt chrome ODS and GRX-10 in the horizontal orientation. And I want to be clear here, on the left is 21 megapascals of stress, and on the right is 41 megapascals. And so, in the GRX-10 case, it's double the stress as compared to just nickel cobalt chrome. And then if you look at the X and Y axis, maybe I'll go to the next slide to better compare it. What's interesting is that the nickel cobalt chrome ODS, again, it is struggling with that severe creep ductility issue that you expect to see with ODS alloys. But for GRX-10, it appears to have overcome this ductility issue that has limited ODS alloys in the past. You have good creep ductility, and just comparing this nickel cobalt chrome ODS to GRX-10, it has significantly better life, much better ductility, and we're in an environment where this is double the stress as the nickel cobalt chrome ODS. And so this is going back a few years. This would have been the property that I think we should have checked first, just to make sure we weren't going to run into this issue. But really excited that it appears that this alloy has overcome a major constraint for ODS alloys beyond just the economics. And so this is a kind of an updated creep overview from the one that you originally show. Again, it has your conventional superalloys here in the red. Here you can see the nickel cobalt chrome ODS in the horizontal orientation. And then here you can see GRX-10 in the horizontal orientation. Still, order of magnitude or more improved compared to your conventional alloys. and significantly better than our ODS nickel cobalt chrome. But as you use this alloy, be aware there is some creep debit depending on your orientation that you're testing here. What's also interesting is that we did see an improvement in the creep properties when we started printing GRX Iten in the larger 3D printers. So this is just comparing, GRX Iten printed in the M280, it's this black curve in the vertical orientation, and then GRX Iten in the M100. And really what this difference is our grain structure in the M280 is coarser. Larger laser spot size produced a coarser grain structure, and that was more optimal for creep. But looking at this, 40 megapascals in the vertical orientation in M280, we're getting life almost to 1,800 hours. And again, this is basically above the stress that you could use any of these conventional alloys with. So it's a pretty phenomenal result here. I really like to show this picture. We want to do a very long creep test for GRX Iten at 3 KSI, so 21 megapascals with the new M280 material. But we had issue because what we were finding is in this test, at least, after 5,000 hours, we had been about 1% creep strain, the sample failed. And it was kind of disappointing because it was sooner than what we were hoping for. But when we opened up the furnace, what ended up failing wasn't the GRX Iten sample. It was actually the load rod that it was attached to. And so, I think this is just, kind of helps, prove the point that, this GRX Iten material is significantly better than a lot of these conventional superalloys. In fact, as we're trying to do these much more elevated temperature testing of GRX Iten, we've actually had to start printing our own test scripts out of GRX Iten to be able to test it. MAR M or Iten 713s are either melting or falling apart at some of these environments. And so I feel like that really kind of drives the point home. We've done a multitude of thermal property testing, CTE, thermal conductivity, and more or less have found in those instances that GRX Iten is comparable to a lot of these other superalloys that you would use. And so these nanoscale oxides aren't adding any showstoppers, especially in thermal properties here. We've also done fatigue properties, both low cycle fatigue and high cycle fatigue. I'm not a fatigue person, per se, so I'm less confident when I'm presenting this data, but I think the most important takeaway is that we haven't compromised our fatigue properties to get these great creep properties. And superalloys in the past, what you usually giving up for better creep is worse fatigue. But because we're getting this great creep properties because of this special composition in the nano oxides, we actually haven't given up any of our fatigue properties. And so in some instances, like high cycle fatigue here on the right, we're comparable, or if not even a little bit better than, let's say 718. And we've done low cycle fatigue up to 2,000 degrees Fahrenheit, and it's done really well. So at least for fatigue, again, comparable, maybe better than other conventional AM superalloys. So that was kind of my quick update. Looking forward, NASA plans to release a preliminary property data sheet for GRX Iten in the next few weeks. We're continuing to do this high temperature testing of GRX Iten, and we've also started testing other conventional alloys and their ODS versions. And so far, GRX Iten has been far and above, even those other conventional ODS alloys and creep at least. It appears to have overcome the severe creep ductility issue that you get with ODS alloys the past few decades, and so I think that even further opens up the application space that you could potentially use this alloy. Again, all of this work has really been done in laser powder bed fusion, and so kind of the next steps we want to look into DED and possibly even other additive methods like wire, and just to see what other components and shapes can we make out of GRX Iten going forward. And so with that, I'd be happy to pass it on to the next speaker.
Thank you very much, Dr. Tim Smith. I want to add that we encourage questions. So if you have one or more, please write down your questions in the questions section of the GoToWebinar display box. The questions will be answered in the question and answer session following the presentations and give all of the presenters a chance to jump in. Thanks again, Tim. Dr. Tim Smith is a materials research engineer at NASA Glenn Research Center. He has a PhD in materials science and engineering from The Ohio State University, and his research focuses on high temperature alloy development and characterization. He has contributed to 29 peer-reviewed publications and has also produced 10 new technology reports and 3 utility patents. He recently received both the Early Career Achievement Medal and the Exceptional Scientific Achievement Medal. Tim's really been a leading researcher in development of dispersion strengthened and high temperature materials, including GRX 810, and it's great to learn from him here today. So thanks again, Tim. Next, we're going to have Paul Gradl present. Paul Gradl is a principal engineer at NASA Marshall Space Flight Center, where he leads projects in additive manufacturing for liquid rocket engines and flight programs for over 20 years. He has authored 135 plus papers, published metal additive manufacturing for propulsion applications in 2022. He holds 5 patents and awarded NASA's 2024 Patent of the Year. He has earned numerous awards, including AIAA's 2022 Engineer of the Year and SME's 2024 Additive Industry Achievement Award. Paul is one of the most influential people in additive manufacturing today, and it's an honor to have him presenting here. Take it away, Paul.
All right, thank you, Jeremy. So Tim highlighted all the material development work, and building upon Tim's work, NASA believes it's very critical to demonstrate these materials in the actual environments and mature the technology readiness. So I'm going to provide some quick highlights on some of that work we've been able to accomplish to achieve a technology readiness level of a 5, potentially a 6. So making this industry and infusion ready. But it's first good to understand what NASA is doing with metal additive manufacturing. We're using metal additive manufacturing across the board for liquid rocket engines, both powder bed fusion techniques and laser powder directed energy deposition techniques, as well as several others. You can see some examples of components on the left-hand side of the slide here: combustion chambers, nozzles, injectors, heat exchangers, rotating components such as turbines, inducers, blisk. On the right-hand side, you see some of the larger scale components, tank components, cases, large-scale nozzles, and then, of course, some of the examples of hot fire testing in the middle. So when we're doing new material development like the GRX 810, we want to move very rapidly into some of these component tests to understand if the properties are going to meet the actual component environment. So very quickly with GRX 810, we picked a couple component applications, one being injectors and another being channel cooled nozzles using the laser powder bed fusion process. And of course, a lot of times we get focused on the powder bed fusion process itself, but when you have to make components and test components, you have to go through a lot of the post-processing as well. And some materials are better processed with like powder cleaning and welding and machining. We want to at least understand from a first order how GRX was going to be processed throughout an entire life cycle. We're currently using GRX 810 in some of our lander development engines and also rotating detonation rocket engines. To date, we have tested several nozzles and injectors that I'll show a little bit later. But I think one of the things that I wanted to point out here are some of the propellants that we're using, both liquid oxygen, liquid hydrogen, and liquid oxygen and liquid methane propellants. You can see an example here of the liquid hydrogen in the upper right and the liquid methane in the bottom right. And we see compatibility with these propellants, and particularly some of the chamber pressures that we've run at, up to about 52 bar in the various mixture ratios. And one of the messages that I think you'll see later as I go through these slides is that the material holds up very, very well in these environments, even when we push it outside of some of the nominal conditions. Like I mentioned, it's really critical, to take the material and these components through the entire fabrication process. And I'll highlight that in a couple slides here. And really, the main purpose of all this testing was to increase what we call the technology readiness level, or the TRL, from just a lab environment, putting it in the actual environment. So, where we're at today with GRX 810 is we're at a minimum of a TRL 5. So we've determined with the GRX 810 that it processes very similar to any of the standard nickel-based superalloys. And I think that's a very good thing. We're not seeing significant challenges in the post-processing by any means. So we follow a very typical flow that we would with any of the other powder bed fusion alloys. Starting with our early design, the actual build operation, the laser powder bed fusion build of, let's say, an injector or a nozzle. We go through extensive powder removal operations and verification of that powder removal, which is an iterative loop. And again, GRX 810, we've not seen any differences at all in that powder removal process. Now, sometimes we will go through a stress relief depending on the component geometry, and then we do removal of the build plate. GRX 810 we've processed in 2 conditions. You can hip the material, and you do get improvements in fatigue life that Tim showed in one of his slides, but we also can process the material and use it in the as-built condition, meaning that there's no heat treatment on that. Typically, we will use in the hip condition, again, just because we get improved fatigue life and some improvements in other properties as well. For some of these components that we develop, we've gone through machining on these, and again, GRX 810 machines similar to some of the standard nickel-based superalloys. We've also developed some of the surface enhancement processes, which I'll highlight in a slide little bit later. And of course, proof testing, cleaning, and then putting this into service. So I think what you see here again is it follows a very typical process flow. There's no unique processing. If anything, there's actually reduced processing on this because you go through a hip and then the material is ready for use. So you don't have to go through any sort of solution or aging or anything that Tim highlighted. So just showing the similar set of steps that I walked through in the prior chart, but actually putting this into pictures of one of our components here, the powder removal and verification of the powder removal, removal of the injector from a build plate post-hip. You notice there's a line on here, but that is tied to breakage of an EDM wire. Flow testing, and then polishing of the face and installation of the face, the injector. Just to hit some quick highlights on this, I'm not going to get into all the details. I'm only showing 5 components here, but I believe we tested upwards of 10 different injectors and nozzles. We have hundreds of starts and thousands of seconds on these components, and typically in rocket engine environments, things can go very wrong in seconds or milliseconds. So this just shows that we've been able to prove out the GRX 810 in the actual environment. And one thing that I want to note in particular here is these injectors and nozzles. The injector that saw 84 starts in over 2,000 seconds, and the nozzle that saw 91 starts. And those are both important to us because when we compare to some of the more traditional materials that we've used for injectors, such as Inconel 625 or Inconel 718, you can see in the bottom left there that we would typically see erosion on these faceplates, injector faceplates after about 10 starts. And one of our injectors in GRX 810, we've made it to 84 starts. So we're seeing improved service life on the GRX 810 material as well. Same thing with nozzles. This is an example of a channel cooled nozzle. So you have all of the channels within the component here. You can see the temperatures that we're pushing on this. Local wall temperatures are above 1000 C, and we're running this continuously for thousands of seconds and have accumulated a lot of time on these components. So again, very robust material in the environments. I do have a quick example here of a rocket engine hot fire test. I don't know how well the video is coming through, but I'll just let it play for a few seconds here. So we have built several different components, as I mentioned, both the injectors and the regen nozzles, but also looking at rotating components as well. So blisk for turbines and different type inducers and blades for some aerospace applications. So we've proven out a lot of the different geometries and thin walls with these components. And again, we see very similar limitations of the powder bed fusion process as you would with any nickel-based superalloy. So I think that again just proves that the material, is more or less production ready. We have developed some other post-processing enhancements as well, particularly surface enhancements. And not going to go into a lot of detail on this. We have some papers that will be coming out very soon on this, but we've applied different processes that you would use to polish the surface, such as electropolishing, chemical milling, chemical mechanical polishing, micromilling, abrasive flow, machining. And again, with each of these techniques, we see very similar results that you'd expect with the more traditional nickel-based superalloys. So the yttria oxide in there is not affecting any of the machinability or any of the post-processing that we would typically use on these additively manufactured materials. Tim provided a little bit of a overview on where we're going with some of the material developments, and I just wanted to iterate a little bit more on this. We will be releasing a lot of data publicly on the material properties. This includes both tensile and fatigue, the creep data that Tim mentioned. And one thing that's been important for us to mature this alloy is to understand both the bulk properties and thin wall properties. So we're completing those studies, and we'll be, again, releasing that data very soon. The elevated temperatures approaching 1300 C that Tim mentioned earlier. In work is the fracture toughness and crack growth, as well as oxidation studies. Additionally, we have several other studies that are really required to mature the alloy and make it production ready and moving towards qualification for flight applications. And this includes the geometric capabilities. We'll have a report coming out on that fairly soon. Build interruptions. So if your part stops in the middle of a build, how do you restart that process, and is the part or component going to be acceptable? So we're looking at some process build interruptions, and we'll provide data on that. The surface enhancements and polishing, and then we have plans to publish future papers on hot isostatic pressing. What is the optimization of the hip cycle that we would use and recommend for the GRX 810? Weldability trials, machinability trials, powder recycling, powder qualification procedures, and then, as Tim mentioned, evaluation of the laser powder DED process. So all of these are in work at some level, and again, be on the lookout for future publications for each of these attributes, as we mature this through the entire supply chain. So at this point, I'm going to hand it back to Jeremy to talk about powder development and qualification.
Thank you, Paul. Sorry, I had to hit my unmute button there. All right, so I'm going to talk about Elementum 3D's commercialization efforts for this material. Elementum 3D is a co-exclusive license holder for commercial distribution of the material. So our commercialization development path has looked at the GRX 810 base material, multiple lots of that, along with the nano yttria material, multiple suppliers and multiple lots of the yttria. We've developed the specifications and testing processes to make sure that we're working with the right constituent materials. And then we've looked at different coating methods and of course settled on one that was working very well that I'll get into the details on, at least the performance. But we looked at actually and did testing on 5 different yttria coating methods to figure out the right way to commercially scale the production of this material. So we looked at a bunch of different ways and found one that's working really well commercially. We had to develop the final product specifications and the production control plans. And then we also looked at the printing process development and making sure that the printed material performed as expected based on the production methods we're looking at. And printed material property testing, we've done a lot of different property testing to qualify our process as well as continue to generate the data that's going to be needed for application of this material. A little bit on our yttria sourcing and evaluation. So you can see from these SEM images that the nano yttria, you can get different morphologies and characteristics from different sources, different suppliers, and different lots. So it's very important that us as a producer have quality control over our yttria sourcing to make sure that we're using the right feedstock so that we get the right consistent performance. And this is something that we're continuing to do analysis on every lot that we use, making sure it meets our quality standards. So as I mentioned, we looked at 5 different commercial scale coating methods and settled on one that's working very well. You can see on the left image the base GRX 810 alloy, and on the right image that's the yttria coated alloy. And we found that our commercial scale coating method produces results that are very comparable to the NASA reference material. Looking at our printed material, NASA did an evaluation where they took powder that we produced, gave to Dr. Smith at NASA, and they did testing, printed this on their EOS M100 system using their parameter set, looked at the microstructure, looked at the as-built density, found greater than 99.97% as-built density, which is very good for any laser powder bed material. And one of the other tests that we did, again at Tim's recommendation, is you can confirm that the yttria is doing its job by looking at the microstructure before and after hot isostatic pressing. At those high temperatures in the hip, you'll get recrystallization if you don't have the yttria there pinning the structure and preventing that recrystallization. So you can see on the left, that's the recrystallized GRX 810 base material if you don't have yttria added. On the right, that is the same as-built microstructure that you get, but it's shown after HIP because it has the yttria included, and the yttria is doing its job. So this really just confirms that the yttria was maintained and is doing its job in the printed material. So as printed with no post-build heat treatment, we wanted to just look at tensile properties at room temperature as a starting point. Even though this is not the primary use case of the material, it's still a good way for us to compare is our commercial scaled material doing what it should compared to the reference material from NASA. And we found that our coated GRX 810 performs in line with NASA's GRX 810 reference material. Both powders are printed by Elementum 3D and our EOS M290 use the same process conditions. And this data here is a limited data set for initial comparisons, looking at just 9 XY direction printed specimens for each test material. And you can see that ultimate yield strengths very comparable. If anything, the Elementum material is in line or even exceeding the reference properties, which is great, and the elongation is spot on in both cases. One other just comment on here is that NASA HIPs everything for additive. The material performs great even without a HIP. It's really an optional HIP, in my opinion, that it performs great with or without a HIP. So now looking at GRX 810 produced in an EOS M290 in the case of the Elementum 3D comparison data, and the NASA reference data produced in EOS M280 system. And looking at the HIP condition, tensile properties at 2000 degrees Fahrenheit or 1093 C. And the Elementum 3D coated GRX 810 again performed in line with the NASA GRX 810 reference material. So this is exactly what we wanted to demonstrate, that the commercial scaled coding and production processes are matching the great NASA data that Tim shared. So X, Y direction specimens as well as Z direction specimens were tested in tensile at 2000 degrees Fahrenheit for the Elementum 3D printed parts, looking again at a limited data set here of 9 specimens each, consisting of 3 different builds and 3 different coated lots of materials. Again, you can see the Elementum 3D coated material is performing, I would say, very in line or even potentially superior to the baseline data. So this is really exciting because this material is fantastic in creep performance, and that's one of the really outstanding characteristics of this material. And we found that in our creep testing, the Elementum 3D coated material is even exceeding NASA's already great creep performance. And you can see in the chart on the left there, that's a creep rupture life test that was done at 3 KSI, rapid rupture creep test. These samples were printed on NASA's EOS M100 system, and the testing was performed by NASA at Glenn Research by Tim and his group. And you can see that the Elementum 3D coated GRX 810 actually had, quite substantially increased creep life, even compared to the already fantastic GRX 810 baseline data there. So that we're really excited to see that not only are we meeting the already great performance, but potentially even exceeding it in a substantial way even. On the right is a creep life curve that Elementum 3D did with an external test lab. We printed both of these materials, reference material and our coated material, and again are finding that our creep life is meeting or even exceeding NASA's already great performance. So I just want to sum up that Elementum 3D is a co-exclusive commercial license holder for NASA's GRX 810, and we have commercial GRX 810 powder available today from Elementum 3D. We have already produced 5 commercial scale lots, and we're ready to supply material to meet the industry's needs. Now I want to open it up to a question and answer session. If you haven't already, please add your questions in the chat, and we'll get to your questions.
So, Jeremy, do you have access to the questions drop down?
I believe so. I'm seeing the ones that you had got in there.
Mm-hmm. Yeah, so I can go ahead and pull some questions here, and then you guys can jump in. So the first question is, are there results from the as printed condition or printed plus HIP?
So the results I shared, if the question's addressed to me, these ones here were as printed with no HIP at room temperature. And then all of the other results are with HIP at temperature. So this is with HIP. And these creep results are also with HIP.
And then I
Okay.
will add that we do have a paper out there which provides some of the initial results on the EOS M280, and we have some additional papers that will be providing that include both the as-built or non-heat treated condition and the HIP condition, and we can send those papers or links out to folks as needed.
Okay, great. The next question is the nickel COCR ODS manufactured by AM processes?
To be clear, you know, all of this work was done through AM, and you know, we haven't really even explored other processes like PM or things like that. So it's kind of almost exclusively AM.
Okay, great. I'm assuming that this question is based on Paul's presentation. He's got on slide 16, is the temperature 1093 Celsius?
Yes, yeah, typically when we're referring to the temperatures, that level, that is Celsius. So we have, I think Tim highlighted that we've completed mechanical testing up to about 1300 C, which is about 2400 Fahrenheit. But a lot of our nominal temperatures that we test for our components are in the 1000 to 1100 C range, or about 2000 degrees Fahrenheit.
Great, thanks, Paul. Next one, the speaker, I'm not sure which one, said that grain boundary carbides are on the scale of 100 nanometers, which is much finer than is usually seen in powder-based AM of nickel alloys. How is the carbide particle size controlled?
You know, I think when it comes to the carbides, you know, it's going to be very sensitive to composition, and so you know, as long as you're within the nominal specs for, you know, GRX A10, I would expect to see the type of carbide sizes that, you know, we were showing. You do see some coarsening of the carbides after operation, but they never you know, really become much larger than maybe like a micron or two, I think. So you know, I think one of the reasons GRX A10 does so well at these elevated temperatures is because of how stable these carbides are. Whereas with a lot of other type of carbides, even, you know, tantalum-rich carbides, chromium-rich carbides, which you would see in a lot of nickel-based superalloys, are much more unstable. They'll you know, solutionize, they'll evolve into other type of phases. The carbides in GRX A10, very stable, evolve very slowly, and help the properties here. So it's very specific to the composition. To be clear, we don't have any type of heat treatment process for the alloy beyond just the HIP steps. So you know, the carbides are kind of just the size that they are.
Okay, thank you very much, appreciate that. The next question, is this alloy suitable for the high temperature rotating components?
You know, I think the way I would answer that is just you got to look at the tensile data, and you have to look at the you know, stresses of those components. You know, I doubt you'll be replacing, you know, CMSX4 single crystal blade alloys with GRX A10 and a commercial jet engine. But there maybe are other applications where, you know, the component could be rotating that maybe it could be suitable. So, you know, yeah, I would. Our hope is, you know, we're getting the data out there so that the designers can make that designation, that determination.
Okay. Next one's hipping. Is hipping a must to reach optimum high temperature fatigue and creep performance of GRX 810?
You know, when it comes to creep, especially in the vertical orientation, you actually get the best creep properties in that as-built state. And so you will see a slight reduction in creep properties with the HIP process. That may be opposite if you're talking about the horizontal orientation. And I do think of fatigue, you know, as with probably every other alloy, closing up some of those defects will improve your fatigue properties. So it's all just depending on, again, your application and what exactly do you need out of the alloy. It's not necessarily a must, but you know, it depends how much risk you're able to tolerate.
Next question. Have you examined the performance of the alloy under creep fatigue interaction, specifically interested in the regenerative cooling applications?
So we do cycle testing on our components. So what we're doing with that is we're taking it through a full hot fire test and then taking it back down to room temperature and repeating that. And I showed some data on injectors and nozzles that we've achieved at least 80 starts, and those are fully cyclic, so fully reversal strains on the specific component. So yes, we have taken that through the components in the hot fire environment. Those are very thin walls as well. So it's probably a little bit more severe than what we'd see in mechanical testing. Also, the transients are very, very rapid in hot fire testing.
Okay. Thank you, Paul. How does the auto ignition property of GRX 810 compare to that of Inconel 718?
So I'm assuming by auto ignition, you might be referring to flammability or promoted combustion. So this is a test where we introduce a material into a pure oxygen environment and you ignite it with like a titanium electrode. And GRX 810 is flammable, but so is Inconel 718. So most of the nickel-based superalloys are going to be flammable in that environment. So to answer the question directly, it would be the same as 718, and you know we would not use either one of those in a pure oxygen environment at elevated temperatures or even at potentially lower temperatures.
All right, before we move forward, our hour is up, but our presenters have agreed to hang on for another 5 or 10 minutes. There are some more questions. So anyone who wants to stay on as we go through some more of these questions, please do so. Next question we got here is for on-Earth applications, 1400 Fahrenheit to 1900 Fahrenheit, is the temperature range of great importance? Could you possibly compare GRX 810 creep strengths to that of alloys such as ABD 900, ABD 1000, ATI 1700?
Yeah, we're kind of starting to work down the temperature. We're doing some 1800F creep and even 1600F. Again, I think at 1800F, you know, we're significantly above at least Haynes 230. You know, I would say I'm hesitant to say there's going to be a lot of application for GRX 10 at 1400 degrees Fahrenheit. You know, those gamma prime strengthened alloys are made for that. 718 works pretty well in that temperature range, and they'll have higher strengths, which will help with the creep properties. So, you know, I would say from 1400 to 1600, there's probably other commercial alloys that you would want to look at first. Then beyond that, 1600F and above, you know, we would want to start making those comparisons. And, you know, as you keep going higher, you're much more likely to be wanting to use GRX 810 versus the other alloys. with those ABD alloys, you want to look at what is the solvent temperature of the gamma prime precipitates. That'll give you a sense of when your tensile and creep properties will drop off. And so if you're below that temperature, it might be worthwhile to use those alloys. If you're above it, definitely consider GRX A10.
Okay, thank you. Next one, could you please share the optimum printing parameters for GRX 810 for 30 and 40 micron layer thicknesses? Jeremy, what do you think about that?
It's something we intend to provide with powder supply, and I know NASA's published on parameters as well that they've used for things. So I believe the information's out there. I don't have it in front of me right now. And,
Okay.
and optimal is also maybe a loaded word. There's many things, are you optimizing for print speed? Are you optimizing for strength, for creep resistance, for density? There's a lot of things to optimize for, but we have a parameter set that's performed well for us that we've used for our data. And I know NASA has parameter sets that they've done a lot of their testing with, including published parameters.
All right. Is the printing process parameters, the workflows, et cetera, bounded by E3D company propriety, or would that be open to the public?
No, we want to help our customers print the material. We want a lot of this material to be printed so that we can sell a lot of powder. So we want to help with parameter sets and other processing properties.
Okay, this question I can answer. Will the presenter's charts be available to attendees? All attendees will be receiving this video version of this Bridging the Gap webinar. So that should be later on today when the recording goes out. Going on to the next question, how much of the improved material properties of GRX 810 are thought to stem from the metastable trigonal oxides compared to grain boundary carbides and other strengthening mechanisms?
That's a pretty loaded question, and something where the answer is evolving, week by week. I think the trigonal oxides are helping just by the fact that we have a finer dispersion of oxides. Again, that should improve your creep properties. I don't think we've done other studies, and so where we also know that the carbides are very critical for high temperature creep strength. So I think it's something you needed a combination of those two plus the base matrix composition. So maybe all three coming together to give the best the creep strength. I think so. Again, I think the oxides are helping. I think the carbides are helping. I think the tungsten and radium segregation, the grain boundaries are helping, and it all leads to a much more robust material at high temperature.
Okay, thanks, Tim. A question did come up about, is there a heat treatment for GRX 810, but I think we've covered that as far as HIP, but not really as solutioning or annealing. Let's move on. Can you recycle the powder between builds?
The answer is yes. Again, almost all the properties that you're seeing here in many cases are done with recycled powder. So Paul will vouch that a ton of our components and samples have been made with recycled powder. But he also mentioned that we need to do that full study just to kind of better understand, are there limits to how many times you can recycle, and things to look out for. And so we're hoping to answer those down the line. But to start with, yes, you can definitely recycle the powder.
Okay, it's good to hear. There was another question that was similar to that, so thank you. Is there an understanding of why creep performance of the Elementum 3D produced powder plus print is improved over the database?
I'm not quite sure. I will say I'm definitely happy to see that. I feel like how many times have we heard the story where you have this great material, but as soon as you scale it up commercially, the properties fall back to earth, and become much less impressive. And so to see it get scaled up commercially and be 2 times better is great to see, and to the point where I feel like I would do a disservice if someone asked for us to provide powder at this point. So I'm not sure, maybe in terms of getting a good dispersion of oxides, the more uniform coating you have, may add to a better bulk material at the end, and that could give you better creep properties, but I'm not positive.
I'll just add that in our testing, when we looked at multiple different coating methods, multiple different process parameters for those coating methods, we did see some differences in the creep performance between those different coating methods. And so, we agree. I think that there is at least a good portion of the factor is probably related to the coating method and the quality of that coating, the ability to retain the yttria.
Okay. Here's a quick one. Will Elementum 3D support development of part printing with GRX 810?
Yes, we want to help customers, especially with prototypes, application development, and so we're very open to that. But we're not trying to be a production partner. We have other contract manufacturers we are happy to work with, and we work with as production partners. But we will help with that initial testing, that initial development, to make sure that you can get the properties, get the part application performance that you need before going to production, either in-house yourselves or with a contract manufacturing partner.
Fantastic. And then another question: how does the cost of GRX compare in cost to other conventional AM nickel-based superalloy powders?
We're happy to discuss pricing based on quantity, separately. So please reach out. I think it's going to be a little bit more expensive than your 718 or your 625. They're really commonly readily available, but there are many other superalloy options that might be more expensive than this as well. So it just depends on what you're comparing against.
All right, and a follow-up on that is, what machines is GRX 810 compatible with at this point?
So we've done work primarily on EOS systems at this point, but there's no reason to think it's not fully compatible with many other systems. And Tim, and Paul, if you want to talk about any other systems that you've worked with, I would say laser powder bed fusion systems in general, I would expect it to be compatible with.
Yeah, that's what I was gonna say. Is our going assumption is if it's laser powder bed fusion, I think it should work out really well. And in terms of other AM processes, we're looking into it some more, and we'll try to come up with optimized parameter sets for possibly those like DED down the road if we get there. But laser powder bed fusion should work fine.
Okay, we just have a couple more questions if the presenters can hang on. Have you seen or performed any prints larger than the 280 and 290? If so, can you speak of the challenges?
We've printed on M400-4, so this is a multi-laser platform. It more or less translated the M280 and 290 parameter set straight to that one. So it worked really well. It was a very seamless process. So again, if it's a laser powder bed fusion machine, I think it should work really well.
Okay, great. And the next question really kind of is based on the answer. Are there challenges with the GRX 810 and other techniques such as DED, powder DED, or wire?
We haven't really given either one technique the attention it needs. With the DED, it depends on what you're trying to build. We definitely had issues trying to do a single wall build with DED in terms of getting the oxides to get incorporated into that single wall. And then, we haven't really explored too much in terms of the bulk printing with DED yet, but that is becoming more of a priority as we go forward, to see, what can we print with DED and what are our properties when we print with DED. When it comes to wire, it's just a matter of, how are you producing the wire and what are those oxides doing? And so there's been some preliminary discussions, but we haven't really done too much with that yet.
Yeah, and the final question is, can you weld GRX 810?
So
we haven't done
So we've done some preliminary welding on GRX 810 using tungsten inert gas or TIG welding, and it welds very similar to the nickel-based superalloys, but we are in process of doing formalized studies such as Veristrength testing and some other weldability studies. But I think first order, it shows that it is weldable, and there's really no challenges with the yttrium oxide in there that we've observed.
I will add, we just recently friction stir welded GRX 810 to Econel 718, so that was another joining method that seemed to work pretty well.
All right, I'll hand it off to, since the Q&A is over, I'll hand it off to Jeremy to close the webinar.
Yeah, thank you. I just wanted to thank our presenters, Dr. Tim Smith and Paul Gradl. Really appreciate your time here and the great information that you gave us today. And thank you everyone else for attending. Appreciate your interest.